So for my project, I chose problem number 2, which was the genetics problem. And so for part 1, we are given 2 equations, which are listed below, and these given variables, which are also listed below. And we have to use Punnett squares to find the frequency of both small p and small q, as well as large P, Q, and R. And so we'll see those on the next slide. And so we find that their total amount of boxes is 12. And for the large AA frequency, there's 2. And the large A small a frequency, there's 8. And the large R frequency, which is those small a's, there are 2. And so we use the equation listed, or the given equation of P equals large P plus 1/2 Q, and small q equals 1/2 large Q plus R. And so we see here that they both equal 6, and with P and Q both equaling 6 out of the 12 total options, that indicates that both small p and small q have a frequency of 0.5 or 50%. And then for part 2, we are asked that if we had a population that had a large AA genotype egg and that had a probability of 0.8 of mating, and a small AA egg type with a probability of 0.2 of mating, and then an egg type of large A, small a that has a probability of mating of 1, what would our frequency of large A in the adult population be? And using Hardy-Weinberg equilibrium, we see that it would be 0.75. The work for that is drawn below, and the answer is highlighted in yellow. And then for part 3, we are given 2 equations, which is that small p plus small q equals 1, and that the function of p equals 0.8 p squared plus 1 times 2pq plus 0.2 q squared. And so with these equations, we will solve both parts A and B. And part A is to show that f of p is also equal to the function listed, and then solve. Part B is to show that is to find the value p hat that maximizes f of p, and we'll do that on the next view. So for part A of part 3, we are going to simplify the given equation or the given function using q equals 1 minus p. So we're going to be plugging in 1 minus p for q, and when you skip a few lines down to the one highlighted in yellow, we have it simplified as negative p squared plus 1.6p plus 0.2. And then we're going to simplify the function that we are supposed to show is equal, and you skip down to the highlighted yellow line and you get 0.2 plus 1.6p minus p squared, and we see that these two are equivalent to each other. And then plugging in 0.5, we see that they both equal 0.75, and we could do that with any other number that was plugged in for p. And then for part B, we're going to find the maximum by finding the first derivative and setting it equal to 0. And so we're going to get p equals 0.8. And then to ensure that this is a maximum rather than a minimum, we are going to use the second derivative rule, which states that the second derivative is solved for and the number is less than 0, it is a maximum, and if it is solved for and it is more than 0, it is a minimum. And so it is -2, which is highlighted in yellow as well, and of course that is less than 0, so that is a maximum. And for part 4, we are going to be showing that the maximum value of f of p occurs at s sub 2 divided by s sub 1 plus s sub 2, as well as that f of p hat equals 1 plus s sub 1 s sub 2 divided by s sub 1 plus s sub 2 is less than 0. And so using these givens, we will plug in 0.8, or we solve to see that p hat of 0.8 is true for this equation, and so we're going to use for S sub 1 negative 0.8 and for S sub 2 negative 0.2, and when you plug those in you get 0.8, which is the given p hat. And then for the second part we are just going to plug in S sub 1 and S sub 2 again, and we get 0.84, which is less than 1. For part 5, we are supposed to be solving for the adult frequency of A and showing that this is the given equation of P1 equals 1 plus S sub 1 times P naught squared plus P naught times 1 minus P naught divided by the function of P naught. And so we will do this using the givens. And so first we have the given for the large A allele and for the large A small a allele. And so if we want to find the total frequency of the large A allele, we will use half of the large A small a allele and all of the large A allele. And so we will do that using half of the given large A small a allele formula. So we will be using P naught Q naught divided by F, or the function of P naught, and then all of the large A allele equation using 1 plus S sub 1 times P naught squared divided by the function of P naught, and we'll add them together and get this equation, which using Q naught equals 1 minus P naught we see is equal to the given equation that we were supposed to show it is equivalent to.